in section 3.7 today, and I think we will stay here for about 15 minutes, maybe 10. And then we're going to section 7.7, the final section of chapter 2B. 7.7. And you'll see why, because you'll get to see it today. Now, technically, the only homework due tomorrow is linearization. However, I'm going to make sure both of them are up online, because when you see section 7.7, you will see why we are going there, and hopefully I can make it clear why we must end there, and we must get there before our final, because it kind of is a grand capstone to everything that we have learned, and it could be helpful for your final exam as well. There is a bonus test review homework, which you might be like, why is it called a bonus test review homework due on Wednesday by 8 a.m.? Because don't we always have test review homeworks due? And don't they always do the day after we finish a chapter? The day of a test. Wait a minute, isn't it you should do the day before a test, and then there's a bonus due the day of the test? But wait a minute, if we're doing a section still today and tomorrow, then that homework will be due on. Do you see things colliding a little bit? Yeah. So it's a bonus test review homework, because ultimately, what's your top priority? Do the homework for the chapter. What's the secondary objective for the quiz on Wednesday? Oh, and review it all. That's the secondary one. That's not the primary. Hence why it's a bonus. So the bonus is optional. The test review is optional. And why are we having a quiz on Wednesday? Because let's just say it's nice to get a good test score in before the end of the semester. And this could be it. Now, it's not a full test. It's not 100 points. If it's a quest, it's 50 points. And once again, it will not be your lowest one. I guarantee you. As long as you adhere and you have done your homework, it will not be your worst one. It should be, maybe even possibly not your best one, because some of you have gotten over hundreds multiple times. However, it should still be a good one, and for most of you, your best one. Because these ones at the very end of the semester, I give a few allowances. All right, Catherine.
Is it going to be the quiz on Wednesday on
3, 5, 3, 6, 3, 7, and 7, 7. 4 sections. 14 identifying optimization, tangent lines / differentials, and then L'Hopital. All of it. Anybody in French? L'Hopital means? Hospital. So, we're going to go ahead and finish up this section, and then start section 7.7, and very possibly we might finish them both today, because I was looking at my notes and the pages, and I think I can go fast. Why would I go fast?
Homework.
You guys could bust out 3, 7, and 7, 7, and then tomorrow can be easy. But forever final on Friday, we know that that's a thing. Plan now Friday to come early, because we want to get a full day of reviewing on Thursday. I would hope at least a half day of review in on Friday, and I'm hoping on Wednesday a half day of review as well. I don't want that quiz to take the whole class, but we'll see. Just remember, I'm giving you derivatives, etc. But in order for us to have at least half a day of review on Friday, you guys need to get in here early to start your forever. Does that make sense? Like a normal test, just get in here early, like a normal test on Friday to get your forever final started. So those of you that are like, sometimes I just come late, please.
Not today, Abby. Not that.
Okay. Okay, here we go. On Friday, we started barely talking about differentials. And differentials, well, we know that dy and dx are called differentials. I've been mentioning that all the way through, coming from differentia, which has to do with derivatives. But quick reminder of where we were before that. Where we were before that was talking about this thing called linearization, not just finding a tangent line, but using a tangent line. Not just finding a tangent line, but using a tangent line. What's all this weird 123 and 121 stuff? Do you guys remember what we were doing? Square root of 123, and I got it correct to 3 decimal places, right? 11.090, but it could have rounded to 1. I got it correct to 10 hundredths thousandths place in my head using a tangent line. Now, yes, I did mental math with a tangent line, which, okay. But you guys could have done it too. And the way you could have done it was right down here as far as we found a function, the square root function, f of x equals square root of x. 123 was very close to 121. So we said, why not make a tangent line at 121, whose square root is 11.090, 11, find his derivative, set up the tangent line. Oh, by the way, with the tangent line, we're solving for the y because the y at the tangent line is being used to approximate. We give that y a snazzy name, L. I think the book calls it T. Did I see that capital T of x, I think? BC book uses capital L of x. Either way, whether you're saying tangent of x or L linearization of x, it's the same thing. It's a new name for the y saying we're going to use you. Well, we're going to use this. And that y will be an approximate for the function. So all this tangent line mumbo jumbo was solving for L, and L was an approximate of the square root of 123, but a dang good one. 11.09090909 when the real one was 11.0905?
Yeah.
Something awkward like that. I just don't remember. Maybe that means I'm the awkward one. So, we were just starting this idea of differential, which you're like, we didn't even finish the section. Well, we kind of did. Because all we didn't do was plug and chug. Well, we didn't plug and chug. And we didn't review something else called who's this guy. This guy, dy, comes from derivative, and all you got to do is just move the dx. dy equals take the derivative and then multiply the dx to the other side. Which might seem really awkward, like, what? You can split those up? But yes, you can split those up. And you can use this to approximate delta y.
Change in y.
Which is change in y. Which we've been doing since last year whenever we would talk about the difference quotient. Because this part of the difference quotient is always representative of delta y. Ew. Hey, forever quiz. Forever final. Oh, we still have some of those in the ceiling. Oops, don't let Mr. House see. Forever final. Isn't this in a forever card? Which forever card is this in? Because it's over delta x and it has a limit attached, and the whole thing put together is equal to who or what? The definition of derivative f prime of x equals what? Limit as h or delta x approaches 0 of f of x plus h minus f of x all over h, or x plus delta x minus f of x all over delta x. We're going to come back to that in just 1 second, but for now, hold on. Did we actually finish this example?
No.
No, because what does it say? Oh. Doesn't it give me, like, numbers? Okay, so how do I find dy? Yes! I take a derivative, and I move the dx to the other side and say, yay, look, dy. But am I done? No, because what do I have to do? Plug and chug. So who would dy be? 1 over 2 root who? 4. Times 3. Isn't 2 times 2 4 and 3 over? Hey, dy is 3/4. Okay. But what else did they tell me to find? And why am I getting out green? Delta y. Okay, well, who is delta y? Okay. Delta y is equal to f of x plus delta x minus f of x. Wait, who is that in context of this problem? Hold on, I didn't plug in anything. Who is my f, guys? Square root of x. So wouldn't f of x plus h be square root of? Are we having to remember maybe some of our definition of derivative skills? F of x plus h or f of x plus delta x says take the f and plug it in, plug it in. And didn't we have to use that for, like, I don't know, solving with the definition of derivative? Or asking nasty limits that needed you to keep going? 0 over 0. Oh, there's a hole, a non-removable removable discontinuity. Anyway, sorry, I'm just reviewing forever cards. Minus square root of x all over. Wait, no, I don't have to do all over. I just have to do the subtraction, right? Oh, okay. Am I done?
Yeah. No.
Plug and chug. Yeah, I have numbers, so plug and chug. This is different. This is new. This is not a limit. Square root of 4 plus. I don't know the square root of 7.
Time to use linearization.
Good thing you know the square root of 4 in a derivative. dy's
2.5.
are used to approximate delta y's. I can figure out how far off I am approximately using a tangent point. But I'm not using a tangent line necessarily. It's kind of a similar idea. I'm saying, I don't know how to get to exactly delta y because I don't know root 7. But I can use a derivative to get to my tangent line and say, they're close. And wherever you are over here, for delta y, which is going to be my, there's my f of x, and there's my f of x plus delta x, and the subtraction between those two, here's my delta x, is going to be approximated by, well, dx, I go over the exact same amount, I'm just going up to a different place. And I don't even think about what they're labeled, I just call that dy. Now, are they going to be the exact same? No. Delta y and dy, there is going to be some error. I'll go get it in a second. There is going to be some error because they're a little bit different, but hey, it's something. Somebody help me out. What's square root of 7 minus 2 on your calculator? Let's see how close we are. There's going to be some error because I went away 3, whereas, well, with 121 and 123, yes, I went away 2, but it was like a leveling off function where it looks stinking linear as it was. This one is a parabola. It gets steeper and steeper. There's going to be some more error. But what is square root of 7 minus 2? 6, 4, what? Sorry, there's more. But yeah. And this one says it's approximately? Is it exact? No. Is it an idea? Yeah. How? I can do a derivative, and I can do a derivative at a point that I know, and it can help me approximate what I don't know. That's the point of differentials. That's not the point of differentials, but that's the application of differentials in this section. Tangent lines, and plug and chug. Now, you could see something having to do with measurement error and percentage error. An application of this whole dy delta y thing. Measurement error. Error can be how far off. How far off. Change in delta. I'm going to say delta M for whatever you're measuring. Delta A for area. Delta V for volume. Delta Y for delta S for measurement of a side. Measurement error is just how far off. Change in whatever you're measuring. M for measuring. So that can change, kind of like delta box, but I thought some of you might get confused by that. Or percentage error is how far off you are of what you're measuring from the total measurement. Let's say you're 2 off, but you're 2 off a measurement of like 3,000. You're pretty close. But let's say you're 2 off a measurement of like 0.5. You're in some serious hot water. That 2 can be a very, very, very slight change, or that 2 can be a very, very, very huge change. It's all based on the percentage. Is it like a 1% plus or minus possible mistake? Or is it like a 200%? That would have been for a half. Yeah. Something like that. 300%? Anyway. So if we're doing something like this, the radius of a sphere is measured with a percent error of radius of a sphere. I think R, if I was identifying variables, R is maybe an important guy. So I have R is my radius. I see V is volume, and by the way, I think I know something about volume, or I could Google it really fast of a sphere. It's 4/3 pi r cubed. Right now, I'm just saying, it's a sphere, there's a radius, there's a volume, okay, this is all I know. But then they give me stuff too. The radius of a sphere is measured with a percentage error of. Who is it that's being measured with that? Radius. So I could say also I'm given delta r all over r is equal to plus or minus 0.04 percent would be 0.0004, right?
Yeah.
Cool. As a ratio. Estimate. We're supposed to estimate the percentage error of volume. So that'd be delta V over V.
What?
Wait, estimating. You think they're giving me a hint that I can use a differential. Ooh. Because differentials estimate changing. Doesn't this mean derivative? So wait, can't I, to find this, can't I start with, okay, well hold on, who is dv? dr. dv dr, why am I writing it like that? Isn't it like dy dx or something?
Running in terms of r.
Yeah, my x is r, my y is v. Can't I take a derivative by bringing down the 3 and I would get 4 pi r squared?
Yeah.
How are we doing? And can't I say, according to what we saw over there, that delta r is the same thing as dr? Remember? If those are the x's, dx and delta x are the exact same thing. So then, couldn't I maybe get my dv alone, because I see him here. dv would equal 4 pi r squared dr. But that's weird. They want me to do percentage error. Isn't that a ratio? But ratios, can't I make ratios? As long as I make sure what I divide on one side, I divide on the other. But well, let's use what seems a bit more applicable. Let's use the v on one side. Let's use what he equals in terms of r on the other side. Now, do we have some simplifying to do? Yeah, a little bit. These 4's are going to end up reducing. I have a 1 over 1/3, which is going to make a 3. These pi's end up reducing. R cubed and r squared will have 1r left. I have 3 dr over r is equal to dv over v. Is that a good thing?
Yes.
Yes. Because can't I come looking and say, hey, they told me about his measurement
What?
error. And I
So
can know exactly how far off my volume. I can estimate how far off my volume is going to be.
So what's 0.004% of 3?
Is that going to be 0.0012, aka? So when you're a little bit off in some sort of measurement, like radius, when you start to use that amount somewhere else, the error compounds. I'm not sure if I want to use the word compound. That's usually in PERT and exponential growth, but the error expands. So what used to be a 0.04% possibility of being off, when I start using this to try to approximate volume, well, I'm going to get farther and farther and farther off. And if I use that volume to do something else, more error and more error and more error. All right, kiddos. The one thing I think we didn't do as far as examples is I just saw down here there was a then sketch that we never did. Lo siento. The then sketch that we never did is the square root of x function, which is a basic graph, going out to 4, wherever that is. And then we have our 2, and then 5, and a 6, and a 7, with that delta x of 3. My delta y would say, hey, let's go ahead and go on over and up. So this little guy, my delta y, would equal root 7 minus root 4. But my dy says, let's look at the tangent line, which I could go ahead and, if I needed to like graph this on my calculator or estimate what it looks like, and I think the skin should be a little bit lower. I could make an equation for him by following that whole tangent line dude, which would be f of c square root of 4, 2 plus f prime of c 1 over 2 root 4, and then times x minus 4. And I'm going to go ahead and not write that as a 2 so you guys can see my tangent line a little bit clearer. Square root of 4 plus. There's my little tangent line if I did need to make an equation for him. But basically, delta y says, I'm going to the curve, and dy says, well, I'm doing the exact same over, but I'm going to the tangent line instead. So that would be dy, which equaled 0.75. Pretty close, just a little bit off. Pretty close, just a little bit off. I think there might be one homework problem where it said to sketch. It's just kind of solidifying that, hey, this guy is going to the tangent and this guy is going to the curve. It's not something for you guys to stress about. It's not something that would be on a quiz. Just kind of like a visualization because some of you are visual learners, so it helps a little bit to get a picture of that whole dy. Oh, too far, I'm sorry. dy delta y thing. dy says, tangent line, I'm going there. Delta y says, curve, I'm going there. And sometimes with this root 7, as we can tell, sometimes going to the curve, we don't know how, but going to the tangent line, we do. Okay, I told you guys 10 to 15, it took us like 15, 20. But we still have time to, oh, look, we're done. There's a couple weird things that could happen. Let's wait until tomorrow because I want you guys to see why the heck we're going to chapter 7, section 7. It used to be a CalcBC and required an AB optional topic, but now it is a CalcAB and BC required topic. It used to be a BC required AB optional topic. Now it is an AB and BC required topic. Why on earth am I going to L'Hopital? Wait a minute. Besides some of you starting to freak out about like how L'Hopital is spelled, it's French. And why does a hat on top of the O is French? Is anything else kind of like a deja vu-ish?
There's infinities.
There are infinities.
And there's 0 to 0.
And there's 0 to 0.
Discontinuity.
Indeterminate.
Limits.
What? They're wait, we haven't seen those since chapter 1. Hey, what's on the final?
Limits, everything from chapter 1 to chapter 4. 3.
Chapter 1.
No, not everything.
And we haven't done limits in so long, we're going to fail. Oh. Okay, well, limits with graphs.
And they
We need to remember when they exist and when they don't exist, and whether the approach and the at are both necessary for continuity, but not for the limit to exist. I can't necessarily answer every single thing and review every single thing with limits right now in section 7.7 because the graphs will still, and the piecewise functions will still mess some of you up. But I can make some of the used to be hard ones easier. Because now you know derivatives. And you didn't in chapter 1. Right?
But on the final, doesn't that mean you're probably going to put on like at least one question, find the limit without using?
Possibly, but in multiple choice, can I dictate how you solve anything, especially in a final when you have a Scantron? So do you have options? Well, you're about to. Indeterminate forms. Now, what are the ones that we saw before? Technically, this one and this one are the most common. And not only are they the most common, they're the most helpful when coming with L'Hopital. Now, all the rest of these, technically, we don't know what the answer is. Infinity minus infinity, you have to ask which one is infinitor. Just kidding. More strong, more powerful? Because maybe it's 0, or maybe it's negative infinity because he's stronger, or maybe it's positive infinity because he's stronger. Indeterminate. 0 times infinity. Now, you might be like 0 times anything is always 0, but wait, remember, it's probably going to 0 and going to infinity, so which one is impacting it more? It's indeterminate.
Disgusting.
0 to 0. Uh-oh, he's going to 0, and he's going to 0. Anything to the 0, put 0 to the 0. Put that in your calculator, it doesn't exist, so we don't know. 1 to the infinity is what? Nope, we don't know. Infinity to the 0 is what? Nope, we don't know. Ah! But there are some things we do know. A positive infinity plus a positive infinity is positive infinity. A negative infinity plus a negative infinity is negative infinity. 0 to the infinity is okay. Awkward. 0 to the negative infinity, which would be the same thing as 1 over 0 to the infinity, which would be 1 over 0, which would be infinity. Anyway, these we can tell. Now, long story short, if we're covering this half a day today and a little bit tomorrow, do you think I'm really, really, really going to expect you to be able to do the hardest ones possible with L'Hopital's? No. I stumped CalcBC on a few this year. But we're going to get the main idea. Get the forever card in and be like, I can use this on the final. That's the point. And, isn't it really cool, like, where'd we start? Limits. Where'd we end?
What?
We at least have indeterminate forms.
Yes.
Main ones for the final. These other ones, there are ways of dealing with them, but long story short, we would need to get them back to one of these two to be able to use L'Hopital's. If we can't get these back to L'Hopital's, back to one of these fraction-y do's, we can't use L'Hopital's. So, the ones that you're going to see on the final are going to be in this already, or be giving you these forms already. In homework, you might see a couple of these weird ones that you would have to do some funny creativeness to get there, but the ones in the final will fall into one of these two categories. Let's go see, well, who is this L'Hopital's rule guy?
Old way.
Wait a minute. That's not L'Hopital's. That's Old Way.
First one's easy.
Let's do it.
Old Way. Wait. Old Way. Oh, wait. The AP used to spell it L'Hopital just like that, but now it's actually spelling it the Madison proper way with the S, right? I think it's the proper way with the S. Although he needs a hat. Sorry.
You say L'Hopital. I was like, where did you write that?
Like low pedals. You can say a hospital if you want, but then all the French people. Anyway.
Did you take French?
L'Hopital.
Coming back.
What language did you take?
This one. What happens if you plug it in?
0 over 0, but then if you do
0 over 0, but then you keep going, right?
do this,
Remember, we don't say equal 0 over 0. Just
18
0 over 0.
and
So we could do like a 2 and an x plus 1 and an x minus 1, and we could say like, let's factor. Because when you factor, can't you? Whoops.
oh that
Nice.
you killed something there.
My brain. Or maybe I woke up your brain because you caught me and you were paying attention. A negative 1 plus a negative 1 is a negative 2 times 2 is a negative 4. We could do it. What if you plug it in? Oh, wait. Oh, infinity minus 1 is infinity, and infinity plus 1 is infinity. Infinity over infinity is 1. No. You kind of have the right idea. The degrees are tied. Isn't a limit to infinity? Hey, that horizontal asymptote card. Isn't that a ratio of leading coefficients? But you have to remember a lot of mathy stuff. What if you plug in 0? E to the 0 is 1. 1 minus 1 is 0. What if you plug in 0? E to the 0 is 1. But that hasn't.
KG.
But you keep going. Why?
Element.
Because even though there are e's, we can still factor differences of square. E to the 2x is e to the x squared. That's e to the x plus 1 and e to the x minus 1. But you had to remember how to factor something with the e in it. Don't worry, I'll cross out the right one this time. E to the 0 is 1. 1 plus 1 is 2. Is it possible? Yes. A little tricky though. But what about this? Oof. I could factor 0 over 0.
Is it a 0?
In previous AP years, before they adjusted the exam about 3 years ago, you would never have seen this on an A-B exam. But now you can. Why?
L'Hopital.
It's impossible to do the old way. The old way,
No workout.
I could factor, but nothing reduced it. He's an Ian. He's an exponential. He's a polynomial. They don't. L'Hopital's rule. What's it say?
This is forever.
Yes, it is our final one of the semester.
Oh, this is so exciting.
This is crazy.
We didn't have an optimization, we didn't have a function identifiers, we didn't need a differential or a tangent line. I'm adding linearization to the tangent line card. But yeah, this is forever number 28.
So what you're telling me is I only have to do
Only
21
one?
cards this week?
Yes.
Wait, what?
Did you memorize the others? No, I think you only have 7.
I have 10.
Oh, dear.
Kyle. Epic Kyle moment.
What? He'll be studying as he writes them.
Exactly. Why do them earlier?
Because credit bonus of completed cards sounds like a great idea with us doing all this rushing.
Wait, is there bonus on the forever final? Well, she just.
There are bonuses. No. Andrea asked a good question. She said, "Are there bonuses on it?" Yes. Are there bonus questions? And what else did I just say?
Oh, completion.
Oh, we getting
Hey! Focus. 5 minutes.
One right.
F and G functions that are differentiable. Wait a minute. Isn't there an if? Something that has to be true first? So I need differentiability to be true on A and B, except possibly where the limit is at. Ooh, it's allowed to not work at the place. Oh, yeah. It's allowed to not work because, look, it says indeterminate form. So F and G have to be good everywhere except where the limit is approaching. It's okay to be messed up there. And not only is it okay to be messed up, in order to use L'Hopital's, I must have an indeterminate form. So differentiable functions must have an indeterminate form. And differentiable, now is not the time. Next semester when the AP is coming is the time. But the AP graders make you not only show differentiable, but also show continuous, which I know if it's differentiable, I know. There was a debate, lots of teachers mad at seminars. Anyway, they took off a point if you didn't show differentiable and continuous. We'll deal with that next semester. For now, what's the main idea? P.S. All the indeterminate forms to make it key. But do you guys see how L'Hopital's has a fraction up here, an F over G? That's why I have to have a 0 over 0 or infinity over infinity. Even if the function is not a fraction and makes an indeterminate, I have to make it look like a fraction to use L'Hopital's rule. I have to make it look like a fraction to use L'Hopital's rule. Now next semester, once again, with the AP coming, we might add or adjust this wording a little bit so that they can't take points off our work. Because technically, the way to get here is by using the limit properties, which says, hey, for a division, I take the limit of the top and I take the limit of the bottom. There's a little bit of awkwardness there, but don't stress too much for right now. For right now, we ended down here with a guy that was impossible to use the old way. But in the last 4 minutes of class, how am I going to show you how L'Hopital's works?
You find the derivative.
I'm going to grab a blue pen to say it's new. And I'm going to go back through all of these 4 examples and show you how L'Hopital would have done it. Well, maybe not him specifically, but his math book that he probably wrote and this thing that he probably put into it. How it would have worked. As soon as I check the differentiability, P.S., they both are. Their derivatives exist, and their derivatives exist around 0. And as soon as I see an indeterminate form that I'm not going to write equals because equals means this doesn't work because this is an error, I can't say equals, but I can be like, hey, it's a thing, look. I can come over here and say, according to L'Hopital's, which is what BC kids would write because they're like, there's another way to keep going. I can take the derivative of the top. Wait, no quotient rule? No quotient rule. L'Hopital's rule says, here's a trick. There's a reason behind it, but here's a trick to help you solve the derivative. You're not solving for the derivative. Here's a trick to solve the limit, and it involves derive the top, derive the bottom. It's not quotient rule. I'm not taking the derivative of the whole thing. No. I'm just looking at the top and saying, I need the limit of the top, please, and the limit of the bottom, please, and there's this property about derivatives that will help me do it. 2e to the 2x over, what's the derivative of x?
1.
E to the u times u prime minus 0. Can I plug it in now?
Yeah.
2 times e to the 0, anything to the 0 is 1. Dun, 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 dun. Really? Yeah, I got your calculators and you can check it. Not right now. We don't have time. But wait, so I could have come back here and said L'Hopital's? How would that have worked? Well, what if I had taken the derivative of the top, 2e to the 2x, all over e to the x? No, I still can't. Wait, what's anything to the 0th power? 1. Oh, and that's 1. 2 times 1 over 1 is. That is so easy. Was that right? Wait, so I can come back here. Wait, this wasn't a keep going one. This was a degree test one. But it's infinity over infinity, which is also indeterminate. So I could have taken a derivative of a top over a bottom. Wait, still infinity over infinity, but check it. Don't those just reduce in 6 over 4 is 3 over 2? What? Wait, so this one is L'Hopital's too? Sorry, I like using cursive. So I could have taken limit x goes to -1 of 4x over 1. No wonder the BC kids kept telling us just to learn derivatives. Because what's 4 over 1? Awkward. Awkward.
I'll go talk a moment.
Oh, I didn't plug in a -1. It's fine. Because plugging in a -1 would have been a -4. Why did I make it take the section 7.7? Because it's limits again, but now that you know derivatives.
It's most of the final calculation. Wait.
Oh my God.
Did you just say the entire?
Actually, most of the final.
Good. Always a long answer part. You want that pressure part.
Yes.
Okay. Kiddos, what are you doing tonight?
Homework. 3.7.
3.7 until you get stuck. Then 7.7. Come on, is it? Look. 7.7 until you get stuck. Sound good?
Study for forever.
Am I making both of them be due tomorrow morning by 8 a.m.?
No.
No. Yes.
No.
Number 1.
What do we want real quick? You guys tell me. Do you want to have like one of them do 3.7 mostly done, blah, 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 or just Wednesday then totally done? Both of them? 3.7, 7.7 test review bonus? What's the danger?
Oh,
You ignore homework. But we're all smart and we're all wise. We're not going to ignore homework, right? Get out of here.
Abby, our president.
Wait until you get stuck and skip